Good morning, everyone. Welcome to the day 3 session. I welcome first Dr.Subhasish Dhal, today's resource person. He is an assistant professor in Department of Computer Science, Indian Institute of Information Technology, Guwahati. He is working in an area of information security, blockchain technology, and deep learning. He also worked in the area of security in RFID, where he has proposed a number of security protocols in his PhD in IIT Kharagpur. Currently, he is working in a blockchain-based healthcare systems. Also, he is exploring deep learning to detect the existence of various patterns in software systems. So today we have a very fruitful resource person and he can share his knowledge with us. I welcome and I give a podium for him. Over to you, sir. Dhal sir.
So thank you, Pratibha, for your nice introduction. I'd like to thanks Dr. Kiran and JNN College of Engineering for inviting me for this faculty development program. Can I share my screen? I'm sharing my screen so that so that my presentation will be visible. So I guess my presentation is visible. So actually, I've been told that to give any topic in blockchain. So I thought consensus algorithm is one interesting topic which is much relevant in this workshop. So the topics that I will cover is a little bit introduction. I know that many of the previous speakers have said many things about the blockchains, but still I want to introduce little bit on blockchain so that it will be little bit. For the sake of my topic. Right. Next, I will define what is consensus is. Then I will abstractly present how consciousness is achieved in how consensus is achieved in general blockchain technology. Okay, then I will present three famous consensus algorithm. One is Byzantine agreement, second one is practical Byzantine fault tolerance algorithm, and third one is proof of work algorithm. Then I will conclude with some remarks. So what is blockchain? So this definition is basically much relevant to this topic. Okay, so according to this definition, a blockchain is basically a decentralized computation and information sharing platform that enables multiple authoritative domains who do not trust each other to cooperate, coordinate, and collaborate in a rational decision-making process. So here you can see the keywords decentralized, do not trust, cooperate, coordinate, collaborate. That means this is a system where there is no such central authority who can take any decision. Okay, there are multiple authority, and those authorities do not have any trust with each other, but still they can cooperatively and collaboratively uh, can coordinate in order to take a decision, in order to take a rational decision in this system, right? So from this definition, you can understand that this definition is basically the basic intuition of our consensus of this topic, right? So before going further, I am going back to a little bit more backgrounds. Okay, so there is a centralized system. The concept of a centralized system is that there is a central authority who will take any kind of decision. So in order to take any kind of decision, the authority do not need to consult with anybody else. Okay, so suppose there is a request of any task has come to it, and whether that task has to be performed or not, that decision has to be taken. So in order to take that decision, the central authority himself will take the decision. Nobody else will involve in this decision taking process. So since it is not consulting with anybody else, this process is a little bit faster than other system. But there is a biggest problem of single point of failure, right? So there is a central authority or a single authority who is responsible for everything, right? Now, if this authority is going to be crashed, or if this authority is somehow failed, then the entire system will be failed. Or in other words, if I say that this authority is say malicious, okay, so he can do anything, anything, any malicious behavior he can do, so that the whole system can be collapsed, right? As a simple example, I can give you the example of a banking system where if you want to transfer some money and the bank server is, for say, at that what particular time is collapsed, okay, or maybe broken down. So in that case, you cannot actually transfer your money. Not only you, all the customers who are there in the bank, who are basically the customer of this banking system, nobody can transfer their money at that particular point of time. So this is the biggest problem of a centralized system. So on the other hand, in a decentralized system, there are multiple parties. Okay, so any kind of decision will not be taken by a single authority, but the decision is basically taken collaboratively, in a in a cooperative manner by all the authority, right? So here, whenever a request for a tax will come, then collaboratively all the authority will take decision whether the task should be performed or that should not be performed. Okay, okay. So in order to do this collaboration or this discussion to come up with a proper decision, of course, it is quite slow in compared to centralized system, because some additional work is involved in this system. But biggest advantage is that there is no single point of failure problem. Okay, even if one authority is getting broken down, all the other authority are there who can take care of the request, right? So if you want to transfer your money and suppose one authority is broken down at that particular point of time, but still some other authorities are there or other servers are there, they will collaboratively take a decision whether your transaction is correct or not, and then they will take final decision that whether your transaction should be passed or not, right? So this is the advantage of decentralized system. But here you can see the main point is all the authority has to collaboratively come into an agreement. Okay, so that means they need to have a consensus among themselves. So blockchain is basically a decentralized approach, as you have already know, because many previous speakers has already told about blockchain. So I am by all the nodes in the network, right? So you can see the blockchain is organized in a decentralized way because whenever some information has to be added into the global data sheet or into these local data sheets, all has to be agreed, okay, and all will collaboratively take decision whether any information will be added into this data sheet or not, right? And another thing, there is no single point of failure problem. Suppose if if this node is crashed or malicious, then still there are some other. Okay. Next, how I am showing how generally blockchain basically works, right? So this is this kind of abstract view of how blockchain works, right? Suppose somebody request for a task, so this request will go to the blockchain network, and all the entity or all the nodes in the network will collaboratively verify the request. If they feel that the request is valid, okay, so they will take decision whether whether that should be executed or not, right? So here, as far as this example, there are four nodes, so everyone is verifying the request, and this node failed that request is correct. These nodes also failed that the request is correct. So every node has failed that the request is correct, so they collaboratively take taking decision that the task will be executed, and the result of the execution will be so a block will be created as the result of that execution, and finally that block will be added into the blockchain, right? So this is the abstract concept how blockchain works. Okay. Now here you can see here multiple parties are collaboratively taking decision whether the task has to be executed or not. Okay. So maybe some parties are here who are not honest or who are faulty. Right. You cannot say that all the parties which are available here all are really honest or non-faulty, okay, but because there may be some party who are not honest, right? So and one important point is these nodes does not know they don't know each other, right? They do not have any trust with each other, okay, still they are collaboratively taking one correct decision. Okay, so it is a challenging, right? So in order to take correct decision, we need to have a proper protocol or set of rules, so that even if there is some malicious or faulty nodes, still correct decisions should be taken by all the honest, collaboratively by all the honest nodes. Okay, so next we are defining formally what is consensus is. So consensus is nothing but reaching agreement distributively in the presence of faults. So there are multiple authority. Among these multiple authorities, some authorities are uh, assumed to be malicious or faulty. Although some authorities are malicious or faulty, but still they should take correct decision, right? So reaching correct agreement or decision distributively in even if in the presence of some faulty or malicious node is called consensus, distributed consensus, right? So this problem was first formulated by Sostakis and Lamport. You can see these papers. So in these papers, basically they have addressed this problem first. They have basically formulated this problem first. So there are some properties of this consensus. Okay, so there are n nodes, each have an input value. Some nodes are assumed as faulty or malicious. So first, according to first property, there is the protocol or the consensus algorithm should terminate after finite amount of time, right? So whatever the protocol have to be designed for this agreement or consensus, that should be terminated, and all honest nodes should reach to an agreement with the same value, right? And according to the next property, agreement property, according to this property, if two honest parties decide on value v or w respectively, then v should be equals to w. What does it mean? If anyone is taking one decision, that means all the honest parties are taking the same decision after termination of the protocol, right? Even so, there will be no difference decision between all the honest parties. And according to the third property, agreed value must have been proposed by some honest node, right? So the decision what has been taken, that should be proposed by some honest node, right? So according to this property, this should not happen that some decision has been taken, but that decision has been proposed by some dishonest or malicious authority, or malicious party or malicious node, right? So this should not be allowed. So you have to design a consensus algorithm such that these three properties should be fulfilled: termination, agreement, and validity. There are many varieties of validity property, but this is a simple form of validity property that everyone will agree upon a whatever the decision will be taken, that will be taken by only the honest node. Okay, so then consensus in blockchain, how consensus basically is performed in blockchain. I can show you some abstract view. So at a particular time, all nodes have a sequence of blocks of transaction they have reached consensus on, and each node has a set of outstanding transaction it's heard about, right? So at a particular time, all the nodes is having a blockchain where all the blocks has already been confirmed or agreed upon through some consensus protocol. Now there are some transactions which has not been confirmed yet, so they are pending. So they are with nodes, and these transaction has to be processed, and they has to be included into a block, and that block has to be added into the blockchain. So a consensus protocol has to be performed between all these nodes, right? So everyone will create some block. So this guy has created this block which is having multiple pending transaction. This guy, similarly, this guy has created one block, and similarly this guy has also created one block. Okay, now a consensus protocol will run among them, and one block will be selected which will be added into the blockchain. So even if one block will be proposed, till that block, if that block is valid, so that block will be added into the blockchain. So according to this consensus protocol, first of all, every nodes will be broadcast to every broadcast their block to every other node, and every node will first verify the transactions on the blocks which they are receiving, and if a block is valid, then that block will be considered for the consensus protocol. Otherwise, that block will be discarded, right? And after completion of execution of the consensus protocol, one block will be selected for adding into the blockchain. So here you can see this block has been selected. This block has been selected after agreement between all these nodes, and it will be added into the blockchain. So in this way, consensus in blockchain basically happens. So this is basically an abstract view how consensus works in blockchain. Okay, but we actually did not see the actual consensus algorithm, right? So we have to design such a consensus algorithm so that the three property of consensus should be fulfilled. So there are some challenges when you have to address when you are designing a consensus algorithm. Okay, so any node may crash anytime. So because of false behavior, any node may be malicious. There is a imperfection in the network. Not all pairs of nodes may be there may not have the availability of point-to-point communication between all the nodes. Okay, so some node may not get or may not receive some blocks. Okay, so that is the problem in traditional network. There may be some faults in network. There may be some latency. Okay, due to due to the delay between one node to another node. So there may be some latency, right? So in traditional network, there is no perfection. So whenever you are designing a consensus algorithm, you have to handle all these challenges, right? So, so there can be a consensus algorithm. Now, how to evaluate the consensus algorithm? So, in order to evaluate the consensus algorithm, or in order to know the quality of the consensus algorithm, these three factors or these three parameters can be used in order to know the quality of the consensus algorithm. According to the first factor, resiliency. According to this factor, it basically express as the fraction of misbehaving parties a protocol can tolerate. That means what is the fraction of the total node who are malicious, and how much fraction of malicious node can be handled or can be tolerated by the proposed protocol, right? So if this value is greater, then that means your protocol is more resilient. If this value is lower, that means your protocol is less resilient, right? The running time. As I've said, that there is a termination property. That means after finite amount of time, your algorithm should be terminated, right? So what is the worst running time for your algorithm that will be seen? That will be basically measured. So running time is uh, another parameter using which we can actually find out the quality of the consensus algorithm. Of course, it is expected that running time should be as low as possible, right? If it will take a huge amount of time, then the overall consensus algorithm or overall decision taking process will take a lot of time, right? Next one is communication complexity. So this basically measure the worst total number of bit or message communicated during a protocol run. So what is the maximum communication need to be there when your protocol will execute, right? So these are the three parameters using which you can judge or you can find out the quality of a consensus protocol, or you can compare multiple consensus protocol to judge which consensus protocol is the best suitable for your problem. So here we discuss three famous protocol: Byzantine Agreement Protocol, Practical Byzantine Fault Tolerance Protocol, Proof of Work Protocol, and there are many other protocols exist in the literature, but it is not. It is of course quite. It is not possible to cover everything. So I hope that these protocols will be interesting to you. Right? So these are the reference of these all these protocols. So let us see one very simple and famous protocol, that is Byzantine Agreement. Okay, before going to discuss the protocol, let's say the definition of a Byzantine node. So a node in the network is said to be a Byzantine node uh, when it has an arbitrary behavior, right? It will not follow the protocol rules. Okay, so in a protocol there is some set of rules, right? So we say that a node is Byzantine node if it will not follow the protocol rules, right? So these are the things a Byzantine node can perform. First one, it will not send any message at all, right? So it has message, but it is not sending any message at all, right? So this behavior is called Byzantine behavior. Uh, Second one is sending different and wrong message to different neighbors, right? So it will receive one message, but it will send or it will forward wrong message, right? So this behavior, if this kind of behavior is there for a given node, then this behavior is also called Byzantine behavior or wrong behavior. And third one is lying about the input value. So suppose it has some input value, but it is lying about that value. So if a node is doing these kind of things, then that node is considered as a Byzantine node or faulty or malicious node, you can say, right? So we'll basically here we'll see one Byzantine agreement protocol, but before to see the algorithm, let us see what is Byzantine agreement. It will be so I'm sharing my whiteboard. I guess my whiteboard is visible. So can somebody confirm that whiteboard is visible or not? Is my whiteboard visible? Can somebody? Yeah. Okay. Yeah. So according to my Byzantine agreement, uh, so there is a general, and they have under this general there are two lieutenants, right? Suppose this general is dishonest or fake, right? So it is fake or faulty, you can say, and these lieutenants are honest, right? Now Now, according to the faulty behavior or Byzantine behavior, it will send different messages to different person. Okay, so for example, this node, this general will send attack message. This general will send attack message to this lieutenant, but is sending retreat message to this node. Right? Clearly, you can see that it is not sending the same message to everybody. So it is the behavior of this node is faulty, right? So it is honest, so it will forward the same message what it has received. It will send attack message, and since this node is honest, it will also forward the same message, that is retreat. Now you consider about this node. If you see this node, it is receiving one message as attack and another message as retreat. Now which message it will believe? Okay, so should it believe at this message or it should believe this message? So it cannot believe anybody, so it cannot reach to a proper decision, right? So you can see if there are three nodes and one node is faulty, then decision is not possible or agreement is not possible. So now I am giving another example where the general is honest and one lieutenant is honest, but uh, but another lieutenant is dishonest, right? It is a fault. Okay, so uh, so since general is honest, it will send same message to everybody. So it is sending attack message to this lieutenant, and also it is sending attack message to this lieutenant. And see, since this is honest, it will forward the same message what it has received. But since this is Byzantine node or faulty node, it will forward a wrong message. That is, it has received attack message, but it will forward retrieved message. Now you can see, if you consider this node, it cannot take any proper decision because it has received attack message from this side and retrieve message from this side. So which message it will believe? There is no way to believe any message, right? So it cannot come to an agreement, right? So agreement is not possible here. So from this example, we can see that if there are three nodes and one node is faulty, okay, then one node is faulty, then agreement cannot be possible, right? So I can draw one relation between this and this. So this is the total number of node involved in the agreement process, and these are the number of node. So I can denote this as n, and I can denote this as f, right? So these are the number of faulty nodes, right? So if this value is less than equals to 3, then so in this case agreement is not possible, is not possible. On the other hand, if 3, we'll see later one example that if 3 is greater than I mean if sorry, if it is 4, then basically decision can be taken. We'll see shortly whether this will happen or not, right? So in general, we can say that if n is less than equals to 3f, then agreement is not possible. I am not giving the formal proof, okay? But by looking into this example, at least we can come to know that if n less than equals to 3f, then agreement is not possible. But we'll see one example where we'll see that if n is greater than equals to 3f, then agreement is possible. So let's say the Byzantine agreement protocol or algorithm. So this is the algorithm, or this is the code for a given node U, where we are considering that there is a single node which is faulty, and for this node the input value is x. So there will be several rounds. In round 1, so this node will send a tuple which is having these two value. This is the identity of the node and the input value. So it will be broadcasted to all the other nodes, and it will receive the similar kind of tuple from all the other nodes in the network, right? So this is the tuple it will receive from the node V. So it will store all the received tuple in some particular set SU. Then at round 2, it will send this stored set of tuple to all the other nodes. It will receive similar way. It will receive the SU, that means set of tuple from all the other nodes. So this is the tuple it has received from node V. So it will create one set of tuple T, where if it will add a tuple if that tuple is visible at least twice, right? If a tuple is not visible at least twice in SU, okay, then it will not be added into T, right? So it will in this way it will generate T. So let this one so this so there is input value, several input values. So according to the protocol rule, they will select one input value as the correct value or agreement value. So in this way, they basically decide on a particular value. So this algorithm will be very much clear if I show the example. So you see, there are multiple nodes. There are 4 nodes we are considering. So N1, the identity of N1 is 1, and the input value is x1. Identity of N2 is 2, input value is x2, and so on, right? So according to the Byzantine agreement algorithm, so they will broadcast their identity and input value to each other. So this will receive this. So this node will receive this value from here. It will receive this value from here, and it will receive this value from here. Right. So similarly, this node will receive this value from here. This value from here, and this value from here. You see, we are considering N4 as the faulty node, right? And N1, N2, N3, they are honest node, right? So your N4 is sending X4 to N1 and N2, but you see it is sending X5 to N3. So it is a malicious behavior, right? It is sending one information to some set of nodes and another information to some other set of nodes, right? So N3 is receiving this information or this type tuple, and N4 will receive this set of tuple. Now, according to page 2, everyone will broadcast their own set of tuples, collected tuples. So this set of tuples will be broadcasted. This set of tuples will be broadcasted. This will be broadcasted, and this will be broadcasted. So this node will receive this tuple. Okay, so this one and this tuple and this tuple. Right. Similarly, this node also will receive a set of tuples. This node will receive a set of tuples. This node will receive a set of tuples. Now you see, it will this node will create the set T, and it will include that tuple which is occurring twice. Right? You can see this tuple is occurring twice. So T for T, it will include one x1, right? And it will include, see it is occurring more than twice, so it will include one x1. So now consider 2x2, it is occurring twice, so it will include into T, and you can see 3x3 is also occurring twice, so it will include this one as well. Okay, but it will not include 4x4 because 4x4 is occurring only once. Similarly, it will not include 4x5. Similarly, it will create tuple, the same set of tuple it will create. It also will create the same set of tuple. And since N1 and N2 and N3 they are honest, this tuple, I mean the value of T, these sets will be same, right? So now according to the protocol rules, they will select the smallest value among all these input values. So suppose the smallest value is x1. So n1 will select s1, x1. So n2 also will select the smallest value, that is x1. n3 also will select the smallest value, that is x1, right? But and this one, since it is a faulty node, it will select either x1, x2, x3, x4, whatever. So you can see that all the honest nodes are agreeing with a single value or correct value, which is x1, right? So from this example, it is we can see that if there are 4 number of nodes and one faulty node, then decision can be taken. So here in this example, you can see that there are 4 nodes and number of faulty nodes. So n is equals to 4, and number of faulty nodes is 1, and 4 is basically greater than 3.1, right? 3 into 1. So I can say that 10 is greater than 3f, or in other words, n. So in this case, agreement is possible. Agreement is possible. But if n is less than equals to 3f, agreement is not possible, right? So this is Byzantine agreement. So there are some lemma and theorem. So if n greater than equals to 4 and f equals to 1, all correct nodes have the same set of T. We have already seen this, although by example. According to theorem 1, Byzantine algorithm for f equals to 1 reaches Byzantine agreement if n is greater than equals to 4. Already we have seen that this is correct, right? So 3 nodes cannot reach Byzantine agreement with all same validity if one node among them is Byzantine. So if there are only 3 nodes, they cannot reach to Byzantine agreement if one node among them is Byzantine or faulty. We have already seen this through the example what I have shown in the whiteboard. And a network with 10 nodes cannot reach Byzantine agreement with f greater than equals to n by 3, right? So this is basically generalization of what I have said here, right? So if I have to prove, suppose total number of nodes can be divided into 3 groups. So group G1, G2, and G3, right? And f number of nodes are Byzantine nodes, right? So the number of element or number of nodes per group is n by 3, right? Now this division will be done in such a way that one group will have minimum one group will have all the faulty nodes, right? So all the faulty nodes will be placed in a single group, right? So if n by 3 is less than equals to f, then I can say that at least one group is full of faulty nodes, right? So suppose this node is full of faulty nodes, and this node may not be some node are honest and some node are dishonest in this group. Similarly, some nodes are honest and some nodes are dishonest in this group. So if you consider the same mechanism, you can say that in this situation agreement is not possible. So in this way you can generalize that if n is less than equals to 3f, agreement is not possible, but if n is greater than 3f, then agreement is possible. So in this way you can prove the theorem. Okay, so next let's see one famous consensus algorithm, that is practical Byzantine fault tolerance algorithm. So this is a famous algorithm. It works in an asynchronous distributed environment. Asynchronous means the delay or out of order message will be allowed. So there may be network delay. Okay, so some nodes may send their response after a huge delay, right? But the system will not wait for a very long time for that message, right? So it will. This algorithm basically can work in asynchronous environment, right? It will handle Byzantine failure. That means the Byzantine behavior, what we have seen, it will handle all the behavior, and it is tamper proof, and it will basically guarantee the authentication. So system model, let us see the system model. According to the system model, there is a single node, and that node is replicated multiple times, right? Whereas there are 3f plus 1 replica in total, including the main node. Right? So there can be one server, and that server will be replicated multiple times, and total number of server or total number of replicas will be 3f plus 1, where f is the number of Byzantine node or server. Right? There will be succession of configuration. So in one configuration, there is single node which is act as a primary node, and all the other nodes act as a secondary node. Right? So one such configuration is called a view. Right? So for a particular view, one node is acting as primary node. Whatever the request will go, all those requests will go to that primary node, and primary node will forward that request to all the other secondary nodes, and they collaboratively or cooperatively take a particular decision, or we can say that they reach agreement collaborative, right? One replica in a view is primary and others are backups, we can say. So this is the algorithm. So this is a three-phase algorithm where we consider there are three plus one number of replicas, where f is the total number of Byzantine node, or you can say malicious node or faulty node, right? So in phase one, the name of this phase is called pre-prepare. In this phase, whenever a request will come to the primary node will prepare one message. So in order to prepare one message, it will assign a sequence number n to the request, uh, and multicast this message. Okay. So in this message, this is the identifier of the message. It identifies that this message is basically pre-prepare message. Right. It consists of these parameters. V is basically view number. What I have said, at particular time there will be one view. Okay, in that view there is a particular primary node and all the other nodes are secondary node. This is sequence number. Why we need sequence number? Because to handle the out of order message, right? Uh, so uh, so some node which is considering some sequence number, it will not handle any other sequence number. And D is basically the message digest. Message digest is nothing but the hash value of the whole message, so that the message which has been sent by the primary or anybody else, primary, that cannot be tampered by anybody else, right? That's why the message digest is there. So it will basically confirm the integrity of the message, right? And the whole message will be signed by the private key of the primary node, right? And the signed message will be broadcasted to all the backups, right? Now all the backups will receive this message and will verify that whether this message is tampered, untampered or not, and they will verify the signature of the current primary node, okay, in a particular view. So if those verification are successful, then they will accept the pre-prepared message, uh, and whenever they will accept the pre-prepared message, they will prepare another message that is called prepare message. So that is why this page is called prepare page. So they will generate a message called prepare. In this message, they will put these parameters. This is view number, similar to this. This is the same sequence number which is used here. This is the digest message digest of this message, right? So once again, the message what has been prepared by the backup, this should not be tampered as well. That's why the message digest has been created and it has been put in within this message. And this is the identity of the backup, right? In this case, the identity of the primary. So it is basically, since it is a pre-prepared message, by default it will be sent by the primary, but this prepared message will be sent by many backup nodes. But which message will belongs to which backup node? In order to identify that, they basically put the identity of them, right? Identity of themselves. And this message is signed by the private key of their own, right? And this message will be broadcasted to everybody, including the primary node. So phase 3 is the commit phase. In this phase, all the nodes basically take decision, or in other words, you can say they basically come to an agreement whether the request will be accepted or not. Right. So if backup will commit, if backup will find at least 2 plus 1 prepare message, which are equal to the prepare message received in phase 1. If it will find that there are at least 2 plus 1 number of prepare message which are equal to the prepare message, then they will commit. Otherwise, they will not commit. Right? We'll see why this value is important. 2 plus 1 is important. We'll see later why 2 plus 1 is really important. Right? So they will commit in this phase, and they will multicast this message. This message consists of this identifier, the view number, sequence number, message digest, and identification information of its own. And this message once again will be signed by its private key. So let us see how basically it will work, right? So you see, one person will request for a task, and this request will go to primary node. So this is our primary node, and these are all backup nodes. Among these backup nodes, these nodes are faulty or malicious nodes, and these blue nodes are honest node, right? So primary node will receive the message. It will generate the pre-prepare message. So this pre-prepare message will be broadcasted to all the backup nodes. You see, it has been broadcasted to all the backup nodes. Now, all the backup nodes will verify this message, and if they will see that this message is correct or not malicious, then they will accept the message and they will prepare one prepare message and broadcast prepare message to everybody to among themselves. You can see this, since this is honest node, it is honestly preparing the message and broadcasting the message to everybody else, right? Similarly, this is also sending or broadcasting the message to everybody else. But since this is not honest, it is silent. Since this is also not honest, so it is also silent. So, so this is a commit stage. If every node will find that there are minimum 12 plus 1 number of prepare message they have received, which is equal to the pre-prepare message, then they will commit, right? Okay. So if then they will prepare commit message and they will broadcast the commit message to everybody else. Now, if everybody in this stage, if everybody will find that they are getting minimum 12 plus 1 number of commit message, then they will confirm and they will reply to the main requester, right? So this node, so this is the primary node. It finds minimum 12 plus 1 number of commit message, so it will reply with the confirmation message. So similarly, this node also sending the confirmation message. But you can see that since this is dishonest, it is not sending any confirmation message. Similarly, this is also not sending any confirmation message. So you can see from this example and this algorithm that the consensus can be reached among multiple party, even if there are some party which are malicious. Okay. Now the question was that why do we need 3 plus 1 number of replicas when there are a maximum f number of nodes are faulty, right? So the answer is that, so if there are 3 plus 1 number of replicas, then we can assume that there are f number of Byzantine node. So so maximum. So we can assume that those f number of Byzantine node will not reply or will be silent. So 2f plus 1 number of node will only reply, right? So among these 12 plus 1 number of node, we actually not sure whether all the 12 plus 1 node are malicious, or maybe it is quite possible that some nodes which has replied, but they are Byzantine node. So you can subtract another f number of node. So the remaining number of node is f plus 1. Okay. Now total number of Byzantine node is f, but here f plus 1 number of node is responding with the same value v, right? Since f plus 1 number of responder is responding with the same value v, if we assume that there are f number of Byzantine node, from this number we can say that there is at least one node which is honest, right? There is at least one node which is honest, and honest node is taking deciding with the value v. Okay, since one honest node is deciding with the value b, and that value will be accepted, or that value will be uh, that value will be the final value as an agreement result, right? So that's why you can say that you can see that we need minimum 3 plus 1 number of replicas in order to successfully execute this algorithm, right? And this discussion also confirmed that why they need 12 plus 1 number of minimum node in order to confirm that that majorities are basically agreed upon the same value, or honest parties are agreed upon the same value. Now, question is if the primary is faulty, okay? So because the gateway is basically the primary node, right? Now, if primary is faulty, then what will happen? So, if primary, maybe primary is the primary node is silent. So, in that case, what will happen? So all the non-faulty replicas together will detect that fault according to this algorithm. Basically, they will check whether they are receiving this kind of message from the primary node or not within some particular amount of time, or within some finite amount of time. If they are not receiving this kind of messages within finite amount of time, okay, then they will assume that probably the primary node is faulty. That's why it is not sending any such message, right? So this is kind of heartbeat mechanism, right? So after every certain amount of time, they will check whether this primary node is still live or not live, right? So if the primary node is not live, that means if they are not receiving any of these messages within finite amount of time, they will go to change the primary node. So there will be some voting. So this will basically ensure the liveness. Even if the primary node is faulty, still the network will be live, because the faulty primary node will be detected, and if the primary node is faulty, then it will basically they will basically collectively select another node which will act as the primary, right? So this PBFT, that is the practical Byzantine fault tolerant algorithm, it basically satisfies the two main property of consensus algorithm, right? So two main property of the consensus algorithm is safety. According to the safety property, they will commit the decision which is proposed by non-faulty node, right? And they will agree with the decision which is taken by all non-faulty replica. And according to liveness property, replicas must move to a new view if they are unable to execute a request, right? So a request has come, but I mean, if primary is fault, then the whole network will maybe broken down. But according to that thing, that view will be, there will be change of view. There is the provision that view will change. So so this liveness property will be fulfilled. So at no time the system will be idle, right? Even if the primary node is faulty. So this is PBFT algorithm. Next, we can see another famous consensus algorithm, that is proof of work algorithm. So before going to know the details of proof of work algorithm, let us see the blockchain in the context of cryptocurrency, one famous cryptocurrency, that is Bitcoin. So in Bitcoin, there will be a blockchain, okay, where this blockchain basically the chain of blocks, where every block is every block are recording all the transactions that had happened in that network, right? So there is the problem called double spending problem, or double spending attack, right? So let's see what is that attack. So you can see at particular point of time, this is the current block, and Alice, suppose Alice is having 50 rupees in her account, and Alice wants to buy some item from Bob, right? And so Alice ordered item from Bob of rupees 50, right? So what Alice will do? Alice will transfer 50 rupees to Bob's account, right? Now, every node in the network will verify this transaction. So at this point of time, Alice had 50 rupees. So this transaction is valid because since in Alice's account there are 50 rupees available, so it is allowed to transfer 50 rupees to Bob, right? So this transaction will be validated, and this transaction will be added into a block, and that block will be added into the blockchain, right? Because this block will be valid, and of course this block will be added into the blockchain. So after addition of this blockchain, uh, Alice should have 0 rupees in her account, and Bob will have 50 should have 50 rupees in his account. But assume that Alice is a malicious person, and it is also a node proposer. Okay, it is also a block proposer, right? So it also can propose block, right? So what Alice will do? Alice will uh, propose this transaction, and will create this transaction, and will add this transaction to this block, right? According to this transaction, Alice is transferring $50 to another account which is owned by himself, but there is some other identity which is used by Alice, right? So $50, 50 rupees is transferred to his own another account, right? So of course, if this block will be proposed, and if this block will be verified by every other nodes, they will verify this, this block successfully, so that because this transaction is valid. Why this transaction is valid? You see, this block has been extended from this block, not from this block, right? It is extended from this block, but not from this block, right? Okay, since this block has been extended from this block, everyone will check the history from this block onwards, right? They will not check these blocks, right? So according to this, the information of this block and the previous blocks, Alice is having 50 rupees in her account. So Alice is of course permitted to transfer this amount to to some other account, right? So this will be validated, and this will be successfully added into the blockchain, right? Now here you can see that Alice had only 50 rupees, okay, but using this 50 rupees, it is transferring or spending twice. Once Alice is spending to Bob, and the same amount of value it is spending to it is transferring to his own account, right? So there are two transactions which has happened. Now, according to the protocol rule of the protocol, that every node will every honest node, okay, will extend block to the longest chain, right? So if you see, this is according. So here you can see there are two chain. This is one chain. This is another chain. If you compare these two chain, this chain is currently longest, right? So if some honest node will propose a block, it will basically extend this chain, not this chain, right? So some honest node will propose block and will extend this chain. So this chain will remain valid. So this chain will not remain valid, but still we'll see what may happen, right? Because Alice has not to go away with the game, right? Alice is still alive with the game, right? So Bob basically in this position after receiving rupees 50, Bob has already dispatched the items to Alice. Okay, and you see Alice may create a few blocks consecutively, and these blocks will be added into this chain, right? Because Alice is not an honest person. Alice Alice will extend the non-longest chain. So Alice will break the rule of the protocol. So breaking the rule of the protocol, it will not extend this chain, but it will extend this chain. Okay, so from here you can see this chain becomes longest, right? So Alice has created several number of blocks, and Alice has created this chain. Okay, so eventually this chain becomes longest than this chain, right? So this chain will be discarded, and this chain will remain valid, right? Now you can see that Bob has already dispatched the item, and since this chain becomes invalid, this transaction will become invalid. So this amount will go from the Bob's account. Why this chain will be invalid? Because you see, at the current point of time, this chain is longest chain. Now, even if some honest party will extend the chain, they will they will extend this chain. They will not exchange this chain. Why? Because at current point of time, this chain is not the longest chain, but this chain is the longest chain, right? So this kind of attack or malicious behavior can be performed if we do not have proper consensus algorithm, right? So Alice, being a malicious node, can perform this malicious behavior if there is no such proper consensus algorithm. So in order to prevent this kind of attack, there is a consensus algorithm that is called proof of work, right? So this proof of work consensus algorithm basically is used in Bitcoin. It is also is used in Ethereum. So these are basically cryptocurrency, famous cryptocurrency, and you can see Ethereum and Bitcoin. They are basically uh, frameworks which is available in the internet, and you can use these frameworks uh, for implement your application, right? There is uh, another consensus algorithm that is called proof of stake, uh, which is usually used in PR coin. This is also another kind of cryptocurrency. Okay, proof of stake consensus algorithm is used in PR coin, right? So according to proof of work, so the node which is proposing a block, okay, so he has to not only propose the block, but also he has not only to propose the correct block, but also he has to show that he has enough resource, right? He has enough computation power, right? He has to prove that he has enough resource or computation power to mine a block, right? In case of proof of stake, the node do not need to show that they have enough computation power, but they have to show that they have enough coins, okay, or they have enough property, right? So let us concentrate on proof of work, uh, which is used in Bitcoin or Ethereum frameworks. So the philosophy of proof of work is the nodes. So multiple, as we have seen that how consensus algorithm basically works in a blockchain. We have seen that multiple nodes are allowed to propose blocks. So multiple nodes are competing among themselves, right? But which node will be selected? Will it be selected randomly? If the block will be selected randomly, then it is there is a possibility that one person will create several IDs, several fake IDs, right? So I will create several fake IDs. Let's say total suppose total number of ID in the network is thousand, I have, and among these 1,000 IDs, I am owning say 900 IDs. So there is total 1,000 IDs, and I am the owner of 900 IDs. Right. So if the proposer will be selected randomly, there is a very high chance that I will be selected as the proposer. Right. So the probability that I will be selected is 900 by 1,000. Right. So this is a very high probability. Right. So so if I choose the proposer randomly, then this double spending, the possibility of double spending attack is very high. Right, because Alice can create several fake IDs, okay, and using these several fake IDs, he will create this fake block or malicious block, and this malicious block will be successful, and she will successfully add these blocks, because the probability that she will be selected is very high in every cases, right? But according to proof of work algorithm, the nodes will not be selected randomly, but they will be selected based on the computing power. Now you see, even if I will create several fake ID, but my computation power is same. Okay, so I have a simple computer, whatever I have a server, okay, whose speed is 1,000 gigahertz, maybe, okay, maybe 1,000 gigahertz, uh, uh, and I am creating 1,000 IDs. So I cannot show that I have 1,000 ID with every ID, every ID using computer with 1,000 gigahertz speed. Right? You cannot. This is not quite possible. Right? This is not at all possible. Right? Uh, So I cannot prove that I have 1,000 ID, and I have 900 IDs, and every ID is having the computer with a similar speed. I cannot prove this, right? So why I cannot prove this? Because I have to solve a hard problem, right? So if I have only one computer with this speed, then I can give only one solution, right? I can give only one solution, say S0. So although I have 900 ID, I cannot provide S0 to S900, 899. 900 solution cannot be generated, because I have only one such computer. Okay, and I have to solve the hard problem using this computer. Right. So I can generate only one solution. I cannot generate 900 solutions. So that's why I cannot prove that I have 900 ID, and 900 ideas are genuine. Right. So according to this consensus algorithm, only the nodes will be selected in proportion to the computing power, and all the nodes will compete for right to create block. Right? Okay, so everyone will have some computation power, and it is assuming that one node, one person is not owning more than 50% of total computing power. So computing power of every node is less than 50% of total computation power. So this is the assumption, underlying assumption. So our underlying assumption is that any node or any person do not have more than 50% of computing resources or computing power of the total computing resources. Okay, so all the nodes are basically competing with each other. So and third philosophy is it basically makes moderately hard to create a new block. So whenever a person has to create a new block, or whenever a node has to create a new block, not only it has to create a valid block, but also it has to solve a hard problem, right? So the problems has to be designed. So this proof of work consensus algorithm basically give such a problem which is moderately hard. Okay, that cannot be solved very easily using a computer or using some resource. So everyone has to solve this hard problem. This problem basically a hash puzzle. So everyone has to solve a hash puzzle. Okay, so so basically they have to compute the hash value. Okay, so parameter of this hash function is the previous hash value. So this this is basically the message digest or hash value of the previous node, which basically acts as the address of the previous node, as well as it help to check the integrity of the previous node, right, and all the pending transaction, right. So using this information, it has to generate the hash value, right? And also, one node has to use one nonce value, right? And they have to generate using this information. They have to generate such a hash value which will satisfy this condition, right? So the hash value should be less than this target value. Some target value will be there, and the hash value should be less than that target value. Suppose target value is in this block is 0, 0, and last bit is 1, and all these bits are basically combination of 0, 1, right? So target value is basically what? 0, 0, 0 up to this last bit is 1, 0, 0, 0, 0. Last bit of this block is 1, and rest of the bits are 0, right? So this is our target value. Now, if somebody has to generate a hash value which is less than this target value, then he has to generate such value where all the bits in this node should be 0, right? All the bits in this block should be 0. Okay, if all the bits in this block will be 0, then of course whatever the bits in this position may be, that value will be less than this target value, right? So target value is this, and if somebody generates such a value where all the bits in this block is 0, and whatever the bits are there in other blocks, that value will be that value will satisfy this condition, and that value will be accepted, and it will be considered as the correct solution of the hard problem, right? But here you can see, in order to generate this value, node has to use previous hash value, the pending transaction. So, and they cannot use arbitrary nonce value. If they will use arbitrary nonce value, it is quite that if somebody is lucky enough, then perhaps they can generate that kind of value which is less than target. But you cannot directly say by given nonce value, you cannot directly generate this value, right? So what you have to do, you have to try every possible nonce, right? You will try nonce as one, and you have to check whether the generated hash value is less than target or not. Or in other words, the generated value consists of all the 0 in this block or not. Then if it will not work, then you have to try nonce value 2. In this way, you have to check all the nonce value, all the possible nonce value. If you are lucky enough, sometimes will maybe will generate some value which is less than the target value, right? So if you are lucky enough, then you can generate this value within a short time, and if you are not lucky enough, then you cannot generate this value within short amount of time, right? So and this also will depend on the computation power. The people who is using the computer with a high computation capability, they can generate this value quickly. whereas who has having less computation power, they can generate this value in uh, less. I mean, they will take less amount of time. So if the people have more computation power, the high probability that they can generate this value, so that they can be the successful person to propose the block, right? But assumption is that the computation power one node is having is not more than 50% of the total computation power, right? So since it does not have more than 50% computation power of the total computation power, uh, it has to compete with others. So it cannot do any monopoly. So you can see that in this example, Alice, although will try to perform malicious behavior, it is very difficult to generate all these consecutive blocks at the same time, uh, because it has limited amount of computation power. That is, it has less than 50% of computation power than total power. So that's why there is very less chance that Alice can generate this set of blocks, so that Alice can generate this chain, right? So this transaction will not be validated. So this transaction will be validated. So Alice cannot perform malicious attack. So double spending attack is not possible, right? So using proof of work consensus algorithm, we can see that uh, the malicious behavior will be discarded, will not be allowed. So only honest party, the decision of the honest party will be added into the blockchain. So if the party is honest, and that party is proposing a block, and if the block is valid, then that block will be added into the blockchain, right? So the we have to design this hash puzzle, right? So we have to design the hash puzzle in such a way that it should satisfy this property. It should be difficult to compute. Why it should be difficult to compute? So that attacker cannot easily compute or quickly compute the solution. Okay, so that attacker will not be the automatic solution, and it should be parameterizable cost. That means node should be automatically recalculate the target. Okay, so target will be adjusted, and it will be trivial to verify, right? So so after generating the target value, uh, so the node will propose the block along with the target value, and every other node will check or verify the target value, whether the solution which has been generated by the proposer is correct or not. So this verification should be easy or trivial. Okay, if this verification is hard, then nobody will try to verify. Right? If nobody will try to verify, the verification will not be successful. So block will not be added into the blockchain. Right? So if this is easy, then everyone will verify. Okay, everyone will interested to verify the blocks. But if it is not easy, if it is difficult, then why I should spare my time, or why I should spare my computation resource in order to verify a correct block where I am not going to get any reward. Now question may come that why at all a person will propose a block, right? So the motivation is that if a person is proposing a block, and if that block is accepted and is added into the blockchain, he will get some reward, right? He will get some reward in terms of some transaction fee or some block reward. Okay, so this is the motivation that one can propose a block, right? But to verify a block, you do not have any such incentive, right? So that is why if this step is hard, then nobody will basically interested to verify. But if it is easy, then every people will be interested to verify the block, right? So whenever you are designing a hard problem, you have to satisfy this property, right? So that we have what we have covered this every topics what I have planned, everything has been covered. Now let us conclude. So we have seen that concept of blockchain basically can be used in many distributed applications. So suppose you are doing some research and you are designing an application, and that application is basically a distributed application, right? So since you are designing a distributed application, you need to have a consensus algorithm. So you can use the concept of blockchain in your uh, distributed application, right? So since your application is distributed application, you need to have a consensus algorithm. So whenever you are designing your application, either you can design your own algorithm or you can use existing consensus algorithm, right? So most of these applications need proper consensus algorithm, right? So so you have to check that whether for your application or for your problem the existing consensus algorithms can be used or not. So there are many existing consensus algorithms available in the literature. So you can try PBFT. PBFT, practical Byzantine fault tolerance algorithm, that is basically used in Hyperledger Fabric or Hyperledger. Some another version of PBFT is used in Hyperledger Fabric, and PBFT is basically used in Hyperledger Sawtooth framework. So if you can design your application using some existing framework, that is Ethereum or Hyperledger or many other frameworks available in the internet or online. So you can use the existing blockchain framework or environment. So if you are using Hyperledger Fabric, then you are basically adopting uh, practical Byzantine fault tolerance algorithm. If you are using Ethereum, that means you are adopting proof of work consensus algorithm, right? So, but if you see that, but you have to take decision which consensus algorithm or which framework you are going to use based on your application requirement, right? So if you feel that any of the existing consensus algorithm is not applicable for your application or for your problem, then you can basically propose your own consensus algorithm. Of course, your own consensus algorithm should satisfy the three properties that I have already mentioned, right? So this is the conclusion. So you can see if you are doing research on any distributed based application, then you can think to apply blockchain concept, and you can use the existing blockchain framework so that you can easily implement your application, because you do not need to uh, arrange any new devices, any new distributed devices. You do not need to use. So existing network of nodes you can use to for experimenting your solution, right? So this is all about what I had to say now. So these are the selected reference. So you can find this book. There is no such book which is available to in this blockchain, but most people basically follow this book. This is kind of preliminary book. This book is written based on cryptocurrency. Okay, and there are some other selected references. You can follow all these references to know more about consensus algorithm. Right? Now mm, I want to take some questions. Thank you. So if somebody has some question, please. I'm stop sharing my screen. So please, um, if you have any question.
Yeah, Dr. Dhal. It was a
Dr.
very wonderful session.
Dr.
It
Kiran,
was
I'm not
complete.
getting your voice actually.
Am I audible now? Dr. Dhal, am I audible? Uh, whether my voice is audible to you?
Hello, Dhal sir, are
Hello?
we audible?
Arun sir, you are audible. Whether my voice is audible to you?
Yes, audible, sir. But
So are
Dhal
you
Dr.
sir,
Dhal?
receiving my audio?
Kiran sir, go
Okay,
ahead.
thank you.
Better.
But I'm not
Yeah.
receiving any voice. Maybe somebody has some question. But anyway, if somebody has any question, please, if you put in chat box so that I can answer all the questions.
Yeah, Dr. Dhal, actually it was quite interesting and it was completely research oriented. So I could able to grasp each and every words what you were telling, like Byzantine things, 3F plus 1, the configuration, and so POW, POS, so all those things I could able to get completely. So probably the beginners, so probably it will be difficult for them to follow. So it's a very good session actually. So you explained why 3F plus 1, because that is a very good. I mean, so most of the people, most of the scholars know that it is 3F plus 1. So but they don't know why it is 3F plus 1. So that is a best part of this workshop. I mean, this session. And so right now we don't have any questions in the chat box. Uh, would you like to say any last word? I mean, would you like to say any concluding words, Dr. Dal?
So, Dr. Kiran, am I audible now? Yeah, but I'm not getting any audio.
Yes, sir, audible. Go ahead, please.
You're audible. Please continue. Would you like to say any concluding words regarding the session? Okay, participants, it seems some network problem. At the end of the session, we faced this one. So luckily, in between, the network was stable. So I wholeheartedly thank Dr. Subhasish Dhal, Assistant Professor, IIIT Guwahati, so for his energetic and slow and steady talk. And he gave insight of consensus algorithms, the one of the vertical of blockchain technology. So the most of the research is happening in this consensus algorithm. So we consider it as like one of the the research field. Okay, and so I would like to personally thank Dr. Dhal for giving the insight about the consensus algorithm POW as well as POS. So that was quite good. Okay. So that's all. So on behalf of NITK as well as on behalf of JNNC, so I thank Dr. Dhal again. Okay. So thank you very much.
Yes, Dr. Kiran. Hello. 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 Yes, yes. Okay, thank you. Yeah, thank you. Yes, yes. Yes, yes, yes. Yes, yes. Yes. Okay. Thank you. Okay. Yes, sure, sure.
Madam,
Yeah,
name is on
thank you.
WhatsApp status, YouTube status.